Hi all. The purpose of this video is for us to go over conceptually what an electric field is and also the relation between electric potential energy and electric potential. So let's start off with our learning goals, and our learning goals are to understand what an electric field is and why it is important in electricity and magnetism, and two, to understand the relationship between electric potential energy and electric potential. So just some electric field facts. And sort of concepts. The first thing is we cannot see just an electric field. It's more of a mathematically useful tool to describe phenomena observed in electricity and magnetism. A couple of E-field facts. They are vectors. They have both a magnitude and a direction. And E-fields obey superposition. So if you look at some point in space, the E-field that could be backtracked out from a measurement of force would be the superposition of all the electric fields from all charged particles creating electric fields at that point in space. So let's start off with something you're a little more familiar with. So we'll have Earth. So we're near Earth. And let's just have some box of mass m, and if we wanted to know what the weight of this box was, it would just be its mass times gravity. So right here we have the force due to gravity near Earth being equal to the mass of the object times g. So you can think of G as being the gravitational field, and it is something that exists everywhere in space, and it's sort of the force per mass. So we could draw gravitational field lines. They all go towards Earth because masses attract each other. And you get the idea. So G has units of newtons per kilogram. So if you multiply G by a kilogram, you get out force. So this is a scalar quantity multiplied by a vector. Now if we take an electricity and magnetism type problem, if we have an infinite sheet of negative charge, then from what you'll eventually see from Gauss's law, we'll get a uniform electric field that points towards the sheet of charge. So everywhere outside it is of uniform electric field strength. These lines should be evenly spaced. Now, if we take some positive charge, say plus Q, put it here, the force on that charge will just be equal to the charge times the electric field at that point. And in this case, it would be a constant quantity anywhere. So it's very much analogous to gravitational fields. So the electric field has units of newtons per coulomb, or it's usually written in terms of volts per meter, but as of right now you may not be incredibly familiar with volts, or since that's something we're going to define later, let's not define it now, but newtons and force pretty good with, coulombs or charge. So that's all well enough and good. Now let's go back to the Earth example. So we have Earth again. We're going to have gravitational field lines coming to the Earth. And we'll again have our box of mass m here. So if we wanted to describe the potential energy of this box, mass m, it's a height h above Earth, then its potential energy, its gravitational potential energy, would be its mass times gravity times height. So you can think of it as its weight times the distance above. So this is the ability for it to do work. So what we know from conservation of energy is, assuming there's no friction or anything, if we wanted to figure out how fast it was going at the bottom, our PE would equal our KE, and our velocity before impact would be just the square root of 2gh, and as you remember, this is independent of mass. So what we could do is we could define a quantity called the gravitational potential. So let's say phi g, and that would be g times h, because this is the quantity that is actually going to determine how much work we can get out of this. So the height above, which is geometrical, and then g, just the strength of the gravitational field. The mass isn't going to really end up determining anything too useful. So this is a way to solve things independent of mass, because in the end, mass just scales up the size of your potential energy, and what really is going to determine the sort of crux of the problem are g and h. So this is, PE per mass. So we could do the exact same thing with the electric field. So we could have our negative charges, we could have electric field, positive Q. So the potential energy will just be Q, E, and then if this is at some height, H, so it'll just be QEH. And then what we can do is define electric potential energy, so charge playing the analogous role of mass. So phi E will just be EH. That's not intentional. So yeah, that kind of gives you a flavor of potential energy, or potential. So this is the potential, this is the potential energy. This is usually written as U. So U equals Q phi E. So what you'll notice is there is a charge that's creating an electric field, but that doesn't come into, but that isn't the charge here. The charge here is the charge that can actually move. So much like we didn't traditionally think about the Earth moving, we thought about the mass falling down. We think about this little test charge as the one that's moving. So it's the charge of this test charge times the potential that is due to this electric field configuration. Thank you very much.